Alright, so now let's look at the motion of the links of a robot. So we have seen how we can basically derive the velocity of a point, and we have also seen how we can basically find out the angular velocity. Now, as we have seen, links are rigid bodies, and they are basically in a robot connected to each other via joints. So each joint actually can be assumed to be a point. So the joint of the links or the origin of the links can be assumed to be points. So we have linear velocities corresponding to those points, and the links can itself rotate also about that point. So we have angular velocities of the links. So each link actually has some linear and angular velocity. But now, since in robotics or in robots we have, if you see on the screen, so it's a typical industrial robot. Now let's say if it's a 6 degrees of freedom robot, it has actually so many links, or I can say six moving links actually that are present. So suppose this is the base, which is attached to the ground via these bolts, and now this is your, for example, link number 1, and this is the link number 2. Then you have link number 3 could be this one, and this is your link number 4. Similarly, you have link number 5, and maybe this rotary part or the end effector is actually link number 6. So here you see you have 6 links attached, or 6 links connected together via joints here, here, and here, and maybe here, and in this way. So each link is actually connected to the other via joints. Only the end effector actually being connected to the previous link on one side, the other side being left for doing particular task. Now each link here actually has the capability to move because of the joints. So it obviously has some linear velocity as a rigid body, and it also has some angular velocity. But because of the constraints or because of the type of joints, those velocities and those linear and angular velocities are actually constrained. You don't have the arbitrary kind of velocities associated with the links, but a particular velocity, linear and angular, as per the joints and the connections. Now, since we know that each link can have some particular linear and angular velocity, that's true, but all these robots, generally industrial robots that we study in this course, actually are what we call as multi-body systems, or they are articulated bodies, which means that the links are connected to each other by joints. So it's not just one body, there are several bodies connected together. So which in turn means, or which in turn would actually mean that the motion of this link, one particular link, actually is not independent, but it's connected to this also. So if this link moves and all the joints are frozen, if this link moves, link 2, which means all the links are also moving, because these are frozen. Link 2 moves, and with its own self it will move all these links. Obviously the relative angle between them may be 0, or we can say that the angle between the two may not change when we freeze them. But if we move 2 and we see that 3, 4, 5, 6 also moves, obviously keeping all this architecture constant. So which means the movement of 2 actually has an impact on the movement of 3, 4, and 5, and 6. Only we can say about 6 that if 6 moves, that may not really have an impact on 5. The motion of 6 doesn't have any impact on 5, but the motion of 5 has an impact on 6. So that's why we have propagation. So velocity, or if you say this way, 1 moves like this, the link 1 moves like this, let's say. So it makes the whole robot move actually like this. So the impact of motion of 1 actually is transferred to the motion of all the other links. So but it's not always that these are frozen, but when we let them free as per their actuators also, So which means that they can be still independently controlled to some extent, but these links are, since they are connected, they are joined by joints. So the link 6, motion of link 6 will be actually dependent on the motion of link 5, 4, 3, 2 and 1 also. All right. So now this thing actually, as we saw it in a line diagram, so it can be shown like this, something like this. We have joints and the links. So the velocity propagates like this from 1 to 2, 2 to 3 and to the end effector. Now we have seen already the how we find out the velocity of the point and the velocity of the basically rigid body. So now we can see how we propagate them from one link to the other link. Now let's assume this is an arbitrary link which has two ends and the structure itself, two ends for the joints. Now there is another link which is connected, so we call this link I and link I plus 1. Now let's attach frames to the links. So we have Z going actually along the axis, ZI. So we'll use the notations by J.J. Craig. And now we see another frame that can be attached to the other link, that is link I plus 1. So accordingly we have ZI plus 1, XI plus 1, YI plus 1. Now there is a vector which is from this origin to the origin of the other frame, that is the position vector here. Okay, so let's take this now to the velocity analysis. Now if you see from the top, so we have omega I plus 1 I. So please be careful here that this type of notation where we have I plus 1 on the right bottom side, subscript side, and I on the left top side, this is not similar to what we had seen for the rotation matrix where we have all the subscript and superscript on the left side, which would actually or specifically mean transformation of some vector from frame B to A, something like that. But in this case has a different meaning. Here it means that omega denotes the angular velocity of link I1 plus 1, link I plus 1 with respect to link I. All right, or you can say that it denotes the angular velocity of link I plus 1 in ith frame. All right, so now in this case if we see, so it means that it's the angular velocity of this link, but because of I it means that it is to be transformed in frame I. So can we represent this in frame I? Yes. So this velocity of this, angular velocity of this, is actually equal to the angular velocity of this link plus the angular velocity of this link with respect to this link, because this link actually impacts the angular velocity of the I plus 1. So the angular velocity I plus 1 would be higher, but it is actually composed of its own angular velocity, its own independent angular velocity, plus the impact of the angular velocity of this. So that's why omega I plus 1 mean angular velocity of link I plus 1 as seen in frame I is equal to omega of link I in its own frame plus omega of I plus 1 with respect to I. So now this is relative velocity. So this is here the relative angular velocity. All right, or you can say the independent velocity of link I plus 1. All right, now this can be written like this. So you have similar terms here, but this can be written like this. So the angular velocity of link I plus 1 with respect to I is actually given by this, because this is the theta dot, because we see in robotics generally we have revolute joints or we have prismatic joints. So let's assume if this is a revolute joint, so we'll have theta dot as the velocity of the link I plus 1, which is its own independent velocity, and its frame. So obviously, the axis. So obviously this is along the joint, or omega we can say. So omega is always along the obviously the joint axis, and the joint axis actually z. So z I plus 1 in I plus 1 only, which is actually 0 0 1. So we can say that it's nothing but 0 0 theta dot I plus 1. Now this is something which can be substituted here, and then we can have transformation from I plus 1 frame to I, which will express everything in actually I. So this is correct. Now we can also define the angular velocity of link I plus 1 in its own frame, which is something like this, but frame has to be its own. So if we do it that way, so which means that the angular velocity that was here, which is the angular velocity of link I in its own frame, has to be back transferred to I plus 1. So I to I plus 1. So at a pre-multiplication with this rotation matrix of this angular velocity vector, plus this will remain without a transformation. Alright, so similarly we have the linear velocity of I plus 1, which means the linear velocity of this joint. The linear velocity of this joint, or you can say this point or the origin of link I plus 1, as seen in frame I, will be equal to linear velocity of the joint I, or you can say the linear velocity of the origin of the link I, alright, plus the omega cross pi plus 1, where pi plus 1 is this. So you can say this is pi plus 1, this one. Obviously when we can say that it has to be in I, because we are measuring from here, we are measuring in I. So pi plus 1 in I, omega cross, because this link is now rotating. So this link has some angular velocity, which is suppose in this case omega I. Obviously this is omega I plus 1 comma I, or maybe you can simply say it's omega I plus 1. So we will not basically try to show it here. So omega I, the rotation of this link with this length will have an impact on the linear velocity of this point. Okay, so that will be now the linear velocity of this point, which is there, which is vi, if it is there, plus omega I cross pi plus 1. Fine. Now this can be again written in its own frame. vi plus 1 in I plus 1 will be pre-multiplication of this whole by ri to I plus 1. Now this leads us to the general expressions for revolute joint and the prismatic joint. For revolute joint, I can say I plus 1 joint I plus 1, we can say like this, which is similar to this expression, and the linear velocity is given by this, which is this expression. And now if the joints are prismatic, so in that case we will see if the joint I plus 1 is prismatic, which means that I plus 1 will not have any rotary motion. If it doesn't have any rotary motion, this goes to 0, which means this part goes to 0. So the angular velocity of link I is will equal to angular velocity of link I plus 1, something like this. Just a transformation matrix, otherwise there is no additional component. But linear velocity will be added, because now this joint can translate. So it will have linear velocity due to the rotation of this, okay, plus the linear velocity of this link, plus it will have its own linear velocity because of the prismatic nature. So that means this will have this whole expression plus di plus 1 dot di, where refers to the joint velocity, or you can say the actual, or you can say the linear velocity of prismatic joint along the prismatic axis. So these are very important and fundamental relations for link propagation for velocity analysis.